This lesson is going to be about limits as x is approaching infinity or negative infinity, and how that ties into being a horizontal asymptote. In our warm-up question right here, we've got a function f of x, we have its graph right here, and we have a table of values as well. And what we want to look at is as x approaches negative infinity, what that means to us is we're going to plug in values of x that are getting smaller and smaller and smaller. So you can see my table, my x values, as I move this way, they're getting smaller and smaller. And what I'm interested in is what the y values are doing. So I can see that my y values are going closer and closer to 2. Even though I stopped this x at negative 5,000, I could have picked a even more negative x, like negative 10,000, and substituted it into this function, and I would have gotten a number that's even closer to 2 than 1.999. So the limit as x approaches negative infinity of f of x is 2. And if I look out at the other direction, as x is approaching infinity, and I make x progressively get larger and larger, I'm interested in seeing what these y's are doing. And I can see as x is getting bigger, as x is growing without bound, I can see that the y values are settling in on this value of 2. And again, even though this table stopped at 5,000, I could have picked 10,000 and plugged it in, and I would have seen a number even closer to 2 than what this one is. So the limit as x is approaching infinity of f of x is going to be 2. And this just confirms what's in this graph as well. And I can see as I move out here, as I move this way on the graph, this is getting closer and closer to a y value of 2. And we talked about these in Algebra 2 as being horizontal asymptotes, and that's what I have right here. So right here at y equals 2, I have a horizontal asymptote, and I can see that as I move to the right, I'm approaching 2 from above, and that's why these values are greater than 2 and getting closer from above 2. And as I move to the left, as x is approaching negative infinity, these y values are getting closer and closer to 2 from below. In Algebra 2, we talked about this and called it end behavior, and it connected what a horizontal asymptote was to a graph. What we're going to be doing now is look at a calculus definition of what a horizontal asymptote is and how limits relate to it. So the limit as x approaches negative infinity, if we settle in on a particular value, or as x approaches positive infinity, if we settle in on a particular value, then that y value is our horizontal asymptote. An important word right here is this word or, because we don't need both of these to happen. We could either have, as I approach negative infinity, or positive infinity. And we will see later on that we don't even have to have the same number for these two values. We could have a different horizontal asymptote on the left side of the graph than we have on the right side of the graph. We're going to learn how to find horizontal asymptotes using limits, the calculus, and also the algebra. There's a lot of algebra involved in this next section. And it all starts with identifying what the dominant term is. And a dominant term is simply the highest power of x. So when I look at this rational function, I look at all the terms, and I'm going to pick out what the highest power of x is, and it ends up being this x to the 4th. So that becomes my dominant term, x to the 4th. And what I'm going to do is divide all terms by this dominant term. Just a little warning, this is going to look worse before it gets better. So just hang in there and understand that we are just developing a concept right here, and it will get better soon. So I'm going to divide each term in my rational expression by x to the 4th. So there we go. Each term has been divided by x to the 4th, and now I'm going to simplify. So the limit as x approaches infinity. And I'm just going to use rules of exponents to simplify each one of these one by one. So it looks a little nicer. So x cubed over x to the 4th is this 1 over x. 5x over x to the 4th is 5 over x cubed. 9 over x to the fourth, nothing simplifies with that guy, so he stays the same. Hey, here's a nice one. X to the fourth over x to the fourth is 1, and so on. You can see the remaining terms. Now I'm going to consider where x is approaching infinity. So the x in each one of these is getting infinitely large. So if I just give you a quick example over here, if I have 1/10, 1 over 100, and I write out fractions, and each new fraction has a denominator that's larger than the previous one, you can see that as each one of these denominators increases, the value of the fraction actually decreases. So in each one of these, 1 over x, if x is getting infinitely large, this is just going to zero out. So all of these where you have the x in the denominator is just going to zero out. So really the only value I have here is the 1. So this equals 0 over 1, which is just 0. So all that work for nothing, literally 0. And also what that's telling me is that this graph right here of that rational function has a horizontal asymptote at y equals 0. Go ahead and pause the video and try example 2 and example 3. You're going to be following the same steps. Identify your dominant term, divide everybody by that dominant term, and then just simplify and evaluate the limit. My first job here is to identify the dominant term. And when I look, I see I have a tie, so it's x cubed. So my dominant term here is x cubed. And so now I'm going to divide each one of these terms by x cubed. And once I've done that, I just simplify. So I'm going to take each one of these terms. Limit as x goes to infinity. That first term here is just going to be a 3 plus 5 over x squared over 4 plus 3 over x. And now I know that x is getting bigger and bigger and bigger. So where I see the x is here, if the denominator is growing without bound, that means the entire fraction will be approaching 0. So that's just going to zero out. That's just going to zero out. And all I'm left with is simply 3 over 4. So that means that this function right here has a horizontal asymptote at y equals 3/4. So I identify my dominant term as x to the 5th, and I divide each term here by my x to the 5th. And after I simplify using properties of exponents, I end up with this expression. And then where each of these have an x in the denominator, that's going to be approaching 0. This is approaching 0, as are these two in the denominator. But this one's a little different because what I'm left with is 5 over 0. And it's not really 0 because I'm just approaching 0. So you can just think it's getting closer and closer to 0. In other words, that denominator is getting really, really, really small. So if I have 5 divided by a really, really small number, what that means is I get a really, really big number, like infinity. And what that means about the limit is it does not exist. In other words, this graph has no horizontal asymptote. It just takes off into infinity. So as the graph gets larger x values, the y values just progressively get larger too. So its end behavior would just kind of be pointing in a northeast sort of direction. Nobody wants to do all that work for each one of these. So down here are the dominant term rules, and we're going to use these from now on. And even though those 3 examples might have felt the same to you, there are actually 3 different distinct cases. So the first case is if you have a dominant numerator, and that happened for us in example 3. In example 3, the dominant term happened to be in the numerator, and whenever that happens, you will get a does not exist for your limit. And what that means is we do not have a horizontal asymptote. If you're looking at a rational expression and your dominant term happens to be in the denominator, dominant denominator, as was the case for example 1, you will always get 0 as your limit value. And what that means is your horizontal asymptote will always be y equals 0. Case number 3 is if you have a tie. If your highest power appears in both numerator and the denominator. And for us, this happened with example 2. And if that's the case, then you make a fraction out of the leading coefficients. So my horizontal asymptote would simply be y equals whatever that fraction is. So just some important information here on the side. So from now on, we're going to use these shortcuts to find limits as x approaches infinity. And realize what we're doing is finding a horizontal asymptote. And also it's important to understand we can only do this is if x is approaching infinity or if x is approaching negative infinity, because that means we're finding horizontal asymptotes. Go ahead and pause the video and do these 4 examples here on the bottom just to make sure you understand it. And just to be clear, we're not doing it the long way. We're going to use those 3 rules that we just talked about. On example 4, the first thing I do is verify that dominant term rules are going to apply. X is approaching infinity, so that means they do. I take a look at all my terms, and I pick where the dominant term is, and my dominant term is this guy right here. It is in the numerator. Whenever your dominant term is in the numerator, that means this limit does not exist. If you find yourself getting these mixed up, just a hint, if you have a dominant numerator, notice that that begins with dn, dominant numerator, and dne begins with dn as well. For example 5, again, I verify that I can use dominant term rules, and I see x is approaching negative infinity. For right now, it doesn't matter if it's infinity or negative infinity. With a rational expression, it's going to be the same either place, so don't get hung up on the negative quite yet. So I'm going to look at all my terms, and I see that I have a tie right here. So here's my dominant terms right here. They both have x cubed. So I'm just going to make a fraction out of the coefficients. Make sure that if there's a negative on the coefficient that you use that negative when you make this fraction. So this becomes -2. For example 6, I take a look at this one, and I see that my dominant term is here in the denominator. And whenever you have a dominant denominator, your answer will always be 0. And my last one here, if your expression is not expanded, we're going to have to multiply this together. So I'm going to go x squared times x and get x cubed, x squared times 8 and get plus 8x squared. I'm only interested in the dominant term, so yes, I need to distribute the -1 through there, but it's not going to affect the answer. All I care about is what the dominant term is, and I've already discovered that. So x cubed here, and I have an x squared in the denominator, which means I have a dominant numerator on this one. So my answer is going to be dne. So again, it's important to understand what we're actually really finding on all of these is a horizontal asymptote for each of these graphs. Verify as you do these limits that x is really approaching infinity or negative infinity, because if it's not, then this doesn't apply. And also make sure that you're using the rules that we developed right here instead of doing it the long way. That was just an effort to show you where these rules are coming from. If you need any help, come see us.